Good morning, guys. How was your weekend? Today, can you hear me? Yes, I can see you can hear me. Thank you. So please register. Those on YouTube should also do same. Uh, Today, I will just give additional information to what I gave you on Friday regarding quantum model of atom. So today, I'm just going to add some information to what I gave you. And already I sent the slides. I sent the slide around 2 to 3:30, 2 to 2:30 p.m. That's to tell you how we work. So you remember we started looking at the current electronic configuration, the way we write electronic configuration that is different from the one you used to know. And so we're going to see the distribution of electrons around the nucleus with different energies. Already I gave information that the current structure of atoms that we know is the major development of the 20th century called quantum theory. I gave information about the work done on light to understand light, and that was now used to understand electrons. Different, many scientists did a lot of work on this, and at the end of the day, they gave us what we know today as a quantum model of atom. Now, I'm adding just one information to it, and that is that this development of quantum theory took place in two stages. So I'm just going to add that briefly. In the first stage, electron was treated as particle. Remember I mentioned this last week. And it was used, that information was used to explain atomic spectra. And it was also used to write electronic configuration of what we know, the old one that you know, 2881, something like that, 21 for lithium. And the second stage, electrons was treated as wave. I also gave this information yesterday. And so when you look at electron as particle, then you are able to determine the exact location and the speed at the same time. But when you look at it as wave, you are not able to determine the exact location. When you have information about the exact location, you are not able to determine the speed. It's too early for this. Who is this? Fagbinro? Fagbinro, unmute yourself. What do you want?
Yes, I can hear you, sir.
You better turn your... I'm shouting here, so maybe it's from your end. Guys, can you hear me? Yes, sir. Thank you. So it's from your end. Pagbenro. Get quality phone and move to Banana Island where they have good signals. And if you cannot get yourself a land in Banana Island, plant banana around your building. We don't have much time. And so that information regarding wave, electron as wave, has been used to study stereochemistry and to do a lot of other information. I will not bother you with how electromagnetic radiation interacts with atoms. But what they did was to look at black radiation. So if you want to understand this, you need to go and look at information about black radiation. It was one of the uh, uh, theory that was put forward. Then you also have the second one, which is photoelectric effect. The emission of electrons from metal surface. So the two, if you go and look at the information from the two, you're going to see that they use them to understand the structure of atom that we know today. And information about German physicist Max Planck, who assumed that energy can either be released or absorbed by atoms only in quantum. But I will not bother you with the calculations. I taught a course that is related to this in year 2. I taught the year 2 students in December, the whole of December, part of November, and maybe the first week in January. So, but I will not ask you to do any calculations in this area. But for them in year 2, they will do a lot of work, a lot of calculations. I have limited time this morning. So you're going to see by the time you look at that note, more information about photoelectric effect and how it has been used to connect to the current atomic structure that we have. And there's something we call threshold. If you shine light on the metal, when the light that you shine on it is enough, when it reaches the threshold of the metal, then the electron will be removed from that metal. So you have that note already. But what I want to teach this morning is completely different from all this. These are just some of the information that was used in arriving at the current model that we have. Now, please put down your hand. That is distracting me. I have a lot of things I'm trying to do this morning because we don't have much time. So distraction by asking questions will be distracting me for now. So if you go and check this information out on Houston, E is equals to HV. I told you I'm not going to bother you about the calculations. Then there was this question that was asked. Is light a wave or does it consist of particles? So that created a lot of doubt. And so to date, the unusual position adopted is to believe that light possesses both wave and particle-like properties. And so you can extend that to electrons, and that is what they've done. They've extended it to electrons, and with that, they've been able to use it to explain a lot of things. If you have a question and you think is relevant, just write it in the chat box. If it's relevant, I will attend to it. Thank you. So that we have a lot of things I want to do this morning. So by the time you look at your note, you're going to see more information. Some of the things that we are going to expect you to just know, you don't have to bother about the details, is what is the difference between continuous spectrum, line spectrum. We have continuous spectrum, there's line spectrum, then emission spectrum, and they've been able to use this to understand what we know today as the atomic structure. Remember, according to Rutherford, you have the nucleus and you have electron moving around. But Bohr took it a step further by saying that electrons revolve in a certain orbit, which implies that it's not in all the orbits that they revolve around in the nucleus. They revolve around certain orbits. So the use of line spectrum was also used to explain this. If you look at rainbow color, you see that you have different colors, but blue merge into green, green into yellow, all of them together. That is a continuous spectrum. But for line spectrum, like you can see in this emission spectrum, you can only see 4 lines. You can see the purple, you can see the blue, you can see the green, and you can see the red. So they use that to explain that, yes, inside an electron, inside an atom, the electrons that we claimed is revolving around the nucleus is revolving in a certain orbit. And that's why you are able to see the different lines. But I would not want to go into details. By the time you read all this, you're going to see all that. And so I gave little information about line spectrum, into little information about continuous spectrum. When the white light that you know, if you see it, you think, yeah, it's just one color. But by the time you pass it through a prism, you see that the white color that you think is just one has different colors. And the white light from a light bulb is dispersed into a spectrum of a continuous range of colors. So which means it's not just one color as you always see it. Now, I've discussed Bohr's model of atom. And I remember mentioning that Bohr started his model by looking at Rutherford model. So there was the acceptance of the picture of atom as a microscopic solar system in which electrons move around the nucleus. Something like that. Okay, you can see the nucleus and you can see electron revolving around it. But in explaining the spectrum of hydrogen, Bohr started with that Rutherford idea, which I've already given you, so I will not want to go into details. So you're going to see other information. I remember giving this information on Friday that according to classical physics, it is believed that as the electron is revolving around, it's losing energy. That a time will come when it's going to spiral, because it's going to lose all its energy. It's going to spiral and move into the nucleus. But that they now observe that uh, law of classical physics has limitation, wasn't able to explain some of the things they observed. So, and that was why Bohr also assumed that prevailing law of physics wasn't adequate. And he assumed that energies are quantized. And he proposed that only orbits of certain radii correspond to certain definitions. So all these are some of the things you're going to see in the note that I've already sent to you. With that, you now know that if you have a nucleus, you have an electron, and you can have an electron there. If you have another shell, you can have another electron revolving around it. And that they are not losing energy to the extent that they will now spiral into the nucleus. Those are some of his assumptions. But there were some limitations to his assumptions as well, which I've already discussed. So I'm not going to bother myself. Then the introduction of the wave behavior of matter. That, okay, Bohr looked at electrons as particles, but the introduction of wave behavior of matter or wave behavior of electron that was introduced now created doubt about Bohr model of atom. And so they abandoned that and moved to the quantum model that we have. So you're going to see all that in the notes. And so de Broglie was able to prove that electron should have properties of wave. And so matter is assumed to have properties of wave. So they were able to use all that information, which I've already discussed. But what I only did was to now sit down and put all information together that can help you understand some of the discussions that I remember also that I pushed across to you on Friday. I remember also talking about uncertainty principle. So the information I gave in these slides now gave clear information about that uncertainty principle and the effect of it on the structure, the current structure that we know. So you will see all that in the note. Then the introduction of quantum mechanics, Schrodinger equation, all these are what I've discussed. So, but what you just see in this note is that I've been able to put further information that will enable you to understand everything. So all you are expected to do it now is to go and sit down, look at the notes, see how you can understand the notes, and now ask yourself as many questions as possible. Draw out questions from the notes and prepare yourself for the test and the exam. Why Bohr looked at electron in one dimension, the introduction of Schrodinger equation made it possible for us to now look at electron in 3 dimensions. And so it was now possible for us to understand a lot of things that we didn't understand using Bohr model of atom. So you're going to see all the consequences of using the current model of atom. Then the addition that I want to add to what you have here is that remember, in Bohr model of atom, only principal quantum number was used. But in quantum model, we have 4 quantum numbers. And so I gave information about them last week. So we have the principal quantum number, which is always represented as n. You have the angular momentum quantum number, which gives information about shape and the different sub-orbitals. Then you have the third one, which is the azimuthal quantum number, the magnetic quantum number, sorry. And so this gives information about the orientation in space. So this information about the orientation in space, but not in their energy. This is the stage where we talk about, if you're looking at P, then you have Px, 2Py, 2Pz. So different orientation. I will not, because of time, I will not be able to go into all. So all you just need to do is to read all this. I'm looking at my watch and I'm trying to see how much I can push across to you. I gave information about this, what is expected. So if you have questions on this, all you are supposed to do is work with others so that you can understand it. Remember, so I'm going to use all these now by the time we get to the next thing I want to discuss this morning, which I'm going to spend a bit of time now. We'll spend 25 minutes, so I'm looking at my work so that I can. Then you have the fourth one that I also mentioned last week. And I told you it can be half, plus half, or minus half. The plus half is the spin up, and the minus half is the spin down. In some textbooks, they will use half arrow, spin up, spin down. So it depends on where you are taking your information from. And I gave some information here. For instance, when n is 1, we did this the other day. What is the L value? What is the shape of the atomic orbiter? What is the ML value? All these are what you are supposed to know. Can you send your answer straight away? If n is 1, what's the L value going to be? The first person that answered that question said 2. 2 is not correct. Yes, 0 is correct because according to the information that I gave you last week, the value of L is taken from the n value. Remember, may take integral value from 0 up to and including n minus 1. So if n is 1, L value is going to be 0. It's going to start from 0 and it will now continue until you get to n minus 1. So an n minus 1 is 0. For instance, if n is 3, L value is going to start from 0. So it's going to be 0, 1, and 2. I gave this information on Friday, so I will not want to waste your time today because of time. So one will expect you, because there is no way you can run away from questions like this in the exam. I will put as many questions as possible in this area as well. While looking at the different dates, I'm going to put questions like this for you to play with in the exam. And if you understand it before you enter the exam hall, conveniently, you'll be able to play with it. So what I did was to just look at that, for instance, and I gave information about if the L value is 0, then that means you have 1s. Oh, okay. Let me also state this. If I tell you n is 2, for instance, then you'll be looking at the level is going to be 2s, 2s, 2p. There's nothing again after that. And so you can now check, what is the L value going to be? If n is 2, L value n is 2. L is going to be 0, 1. And remember, we said for when L is 0, the shape is S. When L is 1, the shape is P. But because the n value is 2, then it's going to be 2s and 2p. If you are looking at when n is 3, for instance, the L value is going to be 0, 1, and 2, based on that information that I gave earlier. And so since n value is 3, then you are talking of 3s, 3p, and 3d. And you now try to do that. And remember, O, when it's 0, the shape is S. When it's 1, the shape is B. When it's 2, the shape is D, and so on and so forth. But you don't have to bother yourself. Just restrict yourself to these few ones and you'll be fine. So you will see it in that table and you can use that, and you can calculate the MS and other values as well. And so I decided to remove the information here to enable you to do some work on yourself by yourself, and you can do all others. So just create time to do it yourself. I'm happy most of you are serious, and that's the reason why I try as much as possible to create the time for this class few minutes to 9. Otherwise, I will not be able to log in to the platform. So if you keep it up, I can assure you that you're going to pass the exam very well. So, and these are questions that you can also practice. So make sure you go through the questions. They are not there just for fun. Now, the next thing is to look at how to write the electronic configuration, which we started last week. So I will only mention that in filling the orbiters, this is the various orbiters that you are supposed to fill. And that is the order. 1s is the lowest. So electron goes into the 1s orbiter without any problem. When 1s is filled up, then the next available orbiter is 2s. And it will continue like that. We use this to address properties of many electrons. We use it to write electronic configuration for many electrons. So you must follow this order in filling the orbitals. And you can see I use red for the first 1, 2, 3, 4, 5, for the first 5 orbitals. After 3p, then there is variation in filling the orbitals, which you must know. Some of you know already, but we assume you don't know. That's why we are pushing this information. And the rules, we have 3 rules guiding the filling of the orbitals. One is what you call off-bar rule. Orbitals are filled in order of energies. You start with the lowest one. So if they tell me to write electronic configuration for sodium, I like sodium, which is number 11. I will use this format. And that is 1s will be filled first, maximum of 2 electrons. You cannot put 3 electrons there. Then the next available orbital after 1s is 2s. So I'm going to put 2s is 2 electrons is maximum that any of them can take. By the time I get to p, from what we've done so far, you know that for p, 3 of them are always available. So you put 6. Each of them will take maximum of 2. So when you look at this now, you have 10 already, and you are going to 11. So the next available orbital after 2p will be 2s. And so I'm going to put 1 there to complete that electronic structure. Then the second rule guiding that is Ohm's rule. That when you have a set of degenerate orbitals that are of equal energy, that's the one we call degenerates, then you fill each of them singly. You fill each of them singly. I tried to do that last week by showing you something like this. Remember, I said if you have oxygen, and oxygen is number 8, then we're going to put 1s2, 2s2, then 2p. We'll now separate the p's, 2px, 2py, 2pz. Remember, I told you that the p are small letters. The p's are small letters, so the s are also small letters. So you have them that way, and you can now also put, so what this rule is telling us is that you are supposed to put 4 electrons in the p orbitals. But what you are supposed to do is to put 1, 1 for each of them first, because they are of equal energy, and that will make them to be stable. Then you can now put the remaining electron into any of the other one. I can put it anywhere because they are of equal energy. I can decide to put it here. And you can also show that by what I've done here. So this will be 2px, 2py, and 2pz. So you must know all this and use that information appropriately. Fasasi, I said, what is it, Fasasi?
Yes, sir. I want to ask a question, sir. Sir, for this Hund's rule, is it only for p orbitals, sir?
For all of them.
All
if
of
we
them.
get to copper, for instance, which is number 24, it's the same thing. We make use of that rule where you have the d orbitals and you spread them accordingly. Because for p orbitals, you have 3 of them that are degenerates. For d orbitals, you have 5 of them that are degenerates. And that's the reason why. So if each of them will take 2 electrons, for d orbitals, the maximum electron that can go into them is 10. For p orbitals, each of them can take 2 maximum. So the maximum electron that can go into any p orbital is 6. And for F orbital, there are 7 in number. So the maximum electron that can go into each of them is 2, 2. And so that will give you 14. So we use that to address the electronic configuration of the lanthanide and the actinides. So these are some of the information. So once you know this, you will be able to write the electronic configuration of all of them. So I said that note already. Then the last one is the one by Pauling exclusion principle, that no 2 electrons can have all the 4 quantum numbers the same. They cannot have all the 4 quantum numbers the same. That's the reason why, you know, in some of them, the ms is going to be plus half, and in the other one, the ms is going to be minus half. So by the time you do it very well, none of them can have the same set of quantum numbers. So once you use the rules very well, you can know. And one other question that one can ask you is, how many unpaired electrons? For instance, if I look at oxygen that I used earlier, remember I said you can use this for 1s, use this for 2s, then you have 2p, 2px, 2py, and 2pz. So for this, is 1s2. So it's complete. So you have one arrow down and one up. Then for 2s is also complete. You have that. Then the next thing will now be px, which we take 1, 1, 1. Then one of them can take the remaining one to make it. You remember what you have is 1s2, 2s2, 2p4. So one of the p's can have one of them to make 4 now. And so that electronic configuration is complete. So they can now ask you, how many unpaired electrons do you have? And you have this. So you're going to say 2 unpaired electrons. And this will make it to be paramagnetic. It will make oxygen to be paramagnetic. It can be attracted by a magnet. That's the meaning of paramagnetic. It can be attracted by a magnet. If it's repelled by a magnet, then you say it's diamagnetic. So oxygen is going to be paramagnetic. If you look at the electron configuration of iron is number 25 or so. Fe is 25. By the time you write the electronic configuration, you're going to see that it's going to be paramagnetic. And that's why iron magnet always attracts iron. Time. So I gave some questions there for you to practice. Then there is what we call condensed electron configuration. Please hold on, Heritage. Send your question via chat. Let me see. In writing the condensed form, assuming I want to write for sodium again. Sodium, you remember, is number 11. Instead of writing it as 1s2, 2s2, 2p6, 3s1, I will look for the nearest noble gas. And if you look at this, that's a noble gas. And what's the name of that noble gas? Neon. So I will just put neon, Ne, the symbol of neon. Put it in a square bracket. Square bracket, I emphasize. There's emphasis on that square bracket. Then 3s1. This is a condensed form. So I can give you something like this in the exam. So get used to all this. And what makes it paramagnetic? Because it has unpaired electrons. Unpaired electrons, once they have unpaired electrons, then they will be paramagnetic. But if the electrons are paired, then they will be diamagnetic. If all the electrons are paired, then they will be diamagnetic. But if you have one of them that is unpaired, then they will be paramagnetic. Thank you. Please, those on YouTube to also register. And I observe that most of them only put their name, they don't put their matric number. If we are looking at attendance, please, it will be difficult for us to put your name again, since we don't have a matric number written or in the attendance. It's going to be difficult for us merging your name with that information. So those on YouTube should also do same. The Zoom guys are doing that now. I hope those on YouTube will also do same. We'll have 15 minutes more. And so we can, I'm very sure with this information now, you'll be able to write the condensed form. And if they want you to write it in condensed form, they will tell you. If we want you to write the complete one, we're also going to tell you. So you should be able to know from the question that will be given to you. Time, guys. I think I have about 80-something slides, and I'm trying to push the 80-something slide across to you. Now, there is also, when we write electronic configuration, we have some anomalous electronic configuration. For instance, chromium. You know, in every case, there's always a Judas. Chromium is number 24. So the electronic configuration, if we use the condensed form, is going to be the condensed form. The nearest noble gas to chromium is argon. So I'm just going to put argon, Ar, square bracket, 4s2, 3d4. Some guys will write it this way, or some guys will write it as Ar, 4s2, 3d5, 4s1, sorry. One of them is correct. The other is not. And the one that is correct is B is correct. A is not correct. So A is not correct. B is correct. And why is B going to be correct? That's Horn's rule that says when you have degenerate orbitals, you must fill all of them singly first before you attempt to fill, before you allow them to pair up. And because already your 4s is paired here, but the d orbital is not complete, so it will not be stable. So this second one, which is B, is more stable than the first one. And so it's going, that's the electronic configuration that is accepted. And it's possible because the energy level of the 4s and the 3d are almost the same. So electron can move into any of the orbitals. You must know all this and make use of the information when asked. The same thing when you look at copper. Copper is number 29. I'm busy. On le pense en time. So I'm very sure you have that information now. So for copper, sorry, there was a little distraction here. Copper is 29. So the same thing is applicable to copper. If you write the electronic configuration, you're going to see that one of them is going to come out as, let me rub up the board. The beauty of my tablet, you can see, I don't need to beg you to come and rub up the board for me. I can do it in the comfort of my room. And I can talk to you, technology. So if you look at this now, 4 is going to be argon. Then you have 4s1, 3d10, or argon 4s2, 3d9. The A is correct. B is not correct. So A is the correct one to show you, and you see this in many electronic configuration. So please note all that, and you can also use it to look at the various ions that is possible. Like copper, one ion is not possible, is not convenient. I don't know why Waris is disturbing me. I said send message. We have limited time, and so I want less distraction for now so that I can still push, because after today, I expect another lecturer to come in so that we can. I said A is the correct one. I did not say B is correct. In this one now, I said A is the correct one. You can see I marked A. I said B is not correct. A is the correct one because the 5d orbitals are degenerate and they are filled completely. So they are filled completely, and so it makes that electronic configuration to be stable. And that you can now use that to explain why copper 1 can exist and why copper 2 plus can also exist. You can use it to explain that. Because when you look at that, electron will leave from the 4s before the 3d. Now, also note, look at the way I've written I also just want to call your attention to that. In some textbooks, they will put 3d before 4s. In some other textbooks, they will put 4s before 3d. The appropriate one is to put 3d before 4s. But that's reason why you put 3d before 4s, I will not want to explain it here. But when you get to calcium, which is number 20, you fill 4s first before you now talk of 3d later. It's only when you get to the transition element that you talk of, you now see the introduction of 3d. How did they write what? Apology, how did they write this? What is this? It's not clear. And for those on YouTube, I can't check information on YouTube. So if there are questions you're asking, I will not be able to answer. But the person that said, how did they write what? Is not clear. Transition element. We're going to look at that now. Sorry about that. I'm introducing a concept that some of you don't know. Copper is a transition element. Chromium is a transition element. So you have to look at, you're going to see this when you, and this we've done already. So you should know how to calculate mass number, proton number, and other things like that. So you see all this in your note. I gave this information before now, and you have all this. So I expect you to do all this. The last thing I want to discuss before I go today, I have like close to 5-10 minutes, is I added this periodic table. We're also expected to know the periodic, because the lecturer that is coming to teach will be looking at the trend. I will not go into details, the story of the history behind periodic table, what Mendeleev did, why today, when we talk of Mendeleev when we talk about periodic table, we always associate the name Mendeleev with periodic table. You're going to see it in the note. His arrangement, he was one of the first few that gave information about how to arrange elements. And he was able to do a lot of work in that area. So I'm going to ask you some questions on it, even the year, and the difference between Mendeleev's periodic table and modern periodic table. For instance, one of the differences is that his own arrangement is based on mass, increase in mass, whereas the current one is based on increase in atomic number. So all these are what you're expected to know. And so go through all these yourself. The only thing I want to add to it is that from the periodic table and from our electronic configuration, for instance, if I told you we've already done that of sodium, which is number 11. And so by writing the electronic configuration, we say 1s2, 2s2, 2p6, 3s1. The last electron is in the s, so is a s block element. For phosphorus, that is number 15. By the time you write the electronic configuration, it's going to be 1s2, 2s2, 2p6, 3s2, 3p3. The last s of electron are in the p, so it's a p block element. The same thing, the d orbitals and the f orbitals. You can see all of them by that time you write their electronic configuration, you're going to see that. So the periodic table, you can look at it in terms of blocks. You can look at the periodic table in terms of elements, whether they arrange electropositive element, electronegative element, and the rest like that. Or in terms of some of them, they have names, family names. We arrange them in terms of group. For instance, if you look at any periodic table, some of the things you're going to see in the periodic table is things like, let me just draw a condensed one. Oh, no, sorry. You should not go that way. You should go this way. Something like that. That's modern periodic table. So you have group 1, so group 1, 2, then the transition elements, group 3 to 12. Then you now have the old group 3, 13, 14, 15, 16, 17, 18. This is where you have the noble gases. Noble gases. You have group 1 here where you have sodium, lithium, sodium, potassium, rubidium, cesium. Then you have the transition element where you have scandium, titanium, and the rest like that. So you need to get a periodic table. You have group 13 where you have boron, aluminium, and the rest like that. Okay? So all these are what you are supposed to know. Then the modern periodic table, you also have below the periodic table, you have 2 sets of elements there, which we refer to as the lanthanide and the actinide. So there's that arrangement in terms of group, like group 1, group 2, group 3. Then there's arrangement in terms of period. For instance, in period 1, you have hydrogen and helium. Look at it. This is group 1 now. Period 1, you have helium. Period. Period runs from left to right. Group run from top to bottom. So this table you are looking at is a modern periodic table. I did not put Mendeleev periodic table here. And when you look at them in terms of block, then you have the S block, group 1 and 2. You have the D block, you have the P block, and you have the F block. All these are what you're going to know. You are supposed to know. So what the teacher that is coming is going to discuss will now be what is expected when you move from lithium to beryllium to boron in terms of size. Are they going to increase in size or decrease in size? What is expected when you move from lithium to cesium, for instance? And remember, you can tell if you have something like this. Remember your old model. Your old model is when you have the nucleus, first shell for lithium, and you say you have 1 electron. By the time you get to sodium, you expect it to be bigger because you're going to have 8 electrons there. And you have additional shell. So it's bigger than this first one. I want to redraw so that people will not think I'm trying to draw covalent something, 1, 2, and 1. And by the time you take the next one, which is potassium, it's going to be bigger. This is 2, 1. This is 2, 8, 1. Then this is 2, 8, 8, 1. So you expect this to be bigger. So we are saying when you go down the group, so these are some of the things that the teacher coming from Wednesday will take you through. So what is the trend when you move across the period? What is the trend when you move down the group? Also, let me quickly call your attention to something here. If you look at that periodic table, hydrogen is put there in group 1 here, but it's not one of them. But it's put in group 1, but it's not one of them. So if we ask you to mention elements in group 1, don't include hydrogen as one of them. It's just put there for convenience, but it's not one of them. By my watch is time. I just want to see if there is maybe 1 or 2 things that I have not mentioned. So look at the table very well. And also know that the groups, they have family name, like group 1, where you have lithium, sodium, potassium. We refer to them as alkali. Group 2, alkaline earth. Group 2, where you have beryllium, magnesium, and the rest like that. We refer to them as alkaline earth metal. And you have the halogens, group 8. Maybe one more thing before you go. So you must know all this. And the transition element, the D block element. They are and you also have inner transition element, the lanthanides and the actinides. So these are the classifications. And so the teacher coming will now try as much as possible to take you through some of the things. It's going to continue from this information that I've given you. Chukwu Funaya. Chukwu Funaya, yeah.
Yes, sir, you were saying that hydrogen.
I can't hear you louder.
I said you were saying that hydrogen is not a group 1 element.
It's too low. I can't hear you. Send a message fast. If you can summarize it or louder.
You're saying that hydrogen is a group 1 element.
It's not a group 1 element, but it's just put there for convenience.
Yes, but when we are talking about valency, like valence is the combining power of elements. Are you with me?
It's not one of them. It's only put in group 1 for convenience because it has 1 electron, but it's not a metal
Yes,
like them.
but in terms of valency, yes, but in terms of valency, they gave hydrogen the properties of group 1 element. Why is it?
We are looking at arrangement of elements now. We are not talking about valency. That's another area of chemistry completely here. Is that clear? You can find time to see me some other time on that. Any other one for now? Heritage. Others are going for another class. But let's hear you, heritage. Heritage.
Sir, how many groups do we now have in the periodic table? Because we were taught 8, but now it is 18 here.
Yes, 8. When you are looking at, thank you, good question. When you are looking at Mendel's periodic table, you're looking at 8. And when I always advise students, when you use that, you use Roman figure because Mendeleev used Roman figure. So Roman figure 1 for group 1, Roman figure 2 for group 2, Roman figure 3 for group 3. But in the modern periodic table, use Arabic numerals 1, 2, 3 to 18. Does that answer your question? Thank
Yes,
you.
sir.
We'll have to go because I'm very sure you guys have another class. Thank you. That's the end of the class. Go through the notes that I've sent to you. I will tell the lecturer to come in to push our lecture across to you. Thank you, guys, for your time. Enjoy. Alade Daniel. Alade, what's the problem? You'll see as she's gone or is gone. It's okay. Thank you, guys. Enjoy the rest of the day. Brown. Brown. Yes.
Sir, I wanted to ask in the exam and test, which version should we go for? Should we use Mendeleev's way of labeling the periods or the modern
We'll
way?
tell you.
Okay, sir.
So if I want you to use Mendeleev, that means I will use I will use the Roman figure.
Okay, sir.
And
Thank
if
you,
I
sir.
want to use the Arabic numerals, then you know I'm talking about the modern periodic table.
Okay, sir. Thank you, sir.
Samuel.
Sir, please, when is the next class?
Wednesday now. The class is going to be on Monday, Wednesday, and Friday, 9 to 10.
Okay, sir.
Today, we are using Wednesday because we have a lot to discuss and we have limited time. So the Wednesday is supposed to be for our lab. And because of the online classes that we're having this semester, we decided to use 9 to 10 of that lab period for this class. Thank you, guys. Enjoy the rest of the day and the week. Bye for now.